Now, for any nuclear reactions that are going to go on or any sort of exchange of particles there, they need to obey certain conservation laws. So we've already got momentum and energy, or mass energy if you like, being conserved. But we've got a few others there. You've done conservation of charge before, so the total charge here before and after a reaction will be the same. The total number of reactants there, their charge should have the same charge as the products. You've also got conservation of baryon number. Now, baryon number then would be an example, would be a proton. That's one baryon. Okay, so that's got a baryon number of 1. Now, since it consists of 3 quarks in, 2 ups and a down, you can think of each of those having a third of a baryon number each, because the 3 of them put together give you a baryon number of 1. Okay, so the quarks there have 1/3, but it gives you the particles as having a baryon number of 1. The anti-quarks, if you had 3 anti-quarks put together there, or sorry, rephrase that. If you had 3 anti-quarks there and an anti-baryon there, you actually get a -1 baryon number. So if you had, say, instead of a proton, you had an anti-proton, that would have a baryon number of -1 because it's an antiparticle. Okay. Don't forget the mesons are actually consisting of particles of matter and antimatter, so you might have a quark with an antiquark, and you'll find their baryon numbers cancel out. It'll be +1/3 and -1/3. So the best thing to do is just try some of these. So I've got some mesons here and baryons here. So if you look at the anti-up quark and the strange quark here, up would be +2/3 electrical charge. So the anti-up would be -2/3 electrical charge, you know, of an E. And the strange one, that's actually the -1/3 normally, because it's in the bottom half. So you've got -3/3 E, or basically it's the equivalent charge of an electron. So that's okay in that count. And just bear in mind for baryon number here, I've got, this is a baryon number of 1/3 then, +1/3 as a baryon, because if you put 3 together you get a full baryon number. But this is an anti one, so that's -1/3 for baryon number, okay? So that will give you a baryon number of 0. And that's okay, that actually works because it's got to be a whole number for baryons. So just keep that in mind. So if I was trying to put a balanced equation with this sort of stuff in it on both sides, I want to make sure that these actually added up correctly together. If you check the up and the anti-up and the 2 strange ones, then you've got a -2/3 again. Strange is actually a -1/3, and -1/3 is... So look at the second particle here, you've got an anti-up, a strange and a strange. So you can see that's still plus a -2/3 for the anti-up, -1/3 for the strange one, another -1/3. Now that's -4/3, so that would not work. You're not going to get a whole charge here, so that's not going to be a particle that actually works there. 2 ups would be a +2/3 and a +2/3, which again is not going to give you a whole charge, so that's not going to work either. And anti-down, now down is normally -1/3, so this would be +1/3. So you've got +1/3 times 3, and that gives you 3/3. You're going to get that, you get 1 + 1 electron there, which is okay for a charge. And finally there, you've got a +2/3 for an up, -1/3 for a down, and the charm one is actually +2/3 if you go and check it on that table. Yep, charm one's +2/3, okay? So you're going to get 2/3, 2/3 is 4/3 -1/3. That actually works. Alright, so that would be okay, but not some of these others. Okay, so you've done conservation of charge and conservation of baryon number. The last one here to look at is the conservation of lepton number. So if you check out, we've done this one here, charge, baryon number, lepton number. So there are 3 lepton numbers to worry about here. First of all is the first generation ones, which are the electrons, so it's called the electron-lepton number. So electrons would have a lepton number of 1, and anti-electrons, or positrons, would have an electron-lepton number of -1. The Electron Neutrino, okay, has also got a lepton number of 1, +1. But the electron anti-neutrino, or the anti-electron neutrino here, would be a -1. So that needs to balance on both sides of the equation. So if you've got electron leptons there, they need to balance on both sides. Now the same thing applies to if you've got muons there, muonic neutrinos. So a muon lepton number needs to be conserved as well. So don't forget that muons have a lepton number of 1, okay? And so would a muonic neutrino particle would also have a number of 1. Whereas an anti-muon particle would be a -1, and an anti-muonic neutrino would also have a -1. So you can't mix these together and say, oh, it's got one electron on one side, which happens to be an electron, and another electron on the other side, which happens to be a muonic one. Those are not going to be balanced. They need to balance with each individual generation. So, in other words, the ones in this column need to be balancing here are lepton numbers, and that's got to be separate from what's going on here and here. So you could actually look at a document here from your textbook. So when you're looking at this here, you look at the lepton names: electron neutrino, tau neutrino, muon neutrino, and so on. This is the symbol for each one. This is the electron lepton number shown here. They're either ones or zeros, and you can see the tau's got a electron lepton number of 0. So is the tau neutrino, so is the muon and the muon neutrino. Okay. Same with the muon lepton number. These have all got a 0 lepton number for muon number, but the muon's got a lepton number of 1, and the muon neutrino's got a lepton number of 1. So even though the electron numbers are here are all saying 1, you've got to be worried about what particular generation they're in. That's got to balance on both sides. Okay? And there's examples here of some anti-ones as well. If you look down there, the positron here has got an E+ symbol as a charge of 1. It's got a -1 electron lepton number though, and 0 for the others. Okay, so let's try and apply some of these conservation laws. Look at this example here. We've got an electron neutrino, or in this case an antineutrino. So in terms of lepton number, we've actually got lepton number that's electronic lepton number of 1 on that side, or -1. Which one? -1, because it's an anti. Okay. You've got a proton here, which is not a lepton. Okay. And you've got a neutron, which is not a lepton. And on this side here, you've got a positron, which is a lepton, and it's actually an electron lepton. Okay. Now, a typical electron has a lepton number of 1. So this particular one has a -1. Okay. So if you check the electron lepton number here, it's the same on both sides. It's -1 plus 0 and 0 plus -1. So the electron number is okay in terms of electron lepton number. If you check the charge here then, the proton has actually got a charge of, now you can actually look at these as tables quite often. So now look at the table here. The proton has a baryon number of 1, a muonic lepton number of 0, a tauonic lepton number of 0, and also an electron lepton number of 0, and it's got a charge of +1. So if we check the charge in here, the charge here, by charge now, we check charge out, you've got a 0, because the electron antineutrino here has got no charge. This has got a charge. On this side now, a neutron doesn't have a charge. I'll say that in the table as well. So it's 0. And the positron has a charge of +1 if you check that out there. So if you check the positron out, the positron here in this table has a symbol of E+, charge of +1. And as I said, electron lepton number of -1 and 0 for the other lepton numbers. So you come back to here then, you've got a charge here of +1. So charge-wise, this is actually balanced. All right. So the last one is to check the baryon number here on both sides. So the baryon number for this lepton here is 0 because it's a lepton. It's not a baryon. It's not a part of the nuclear particles there. Proton has a baryon number of 1. And on the other side here, we've got a neutron, which is also a baryon because it's a nuclear particle there. So that's 1 there. And again, the positron is a lepton rather than a baryon. So if you check both sides of the equation there, that's actually balanced. So this equation would be possible then on that count. All right. Just bear in mind that this is a baryon because it's made of 3 quarks. This is a baryon because it's made of 3 quarks as well, whereas mesons are only made of 2. So I've got a couple of equations to try here as well, look at conservation. So we've got a pion plus particle here, we've got a proton, and if you look down here, we've got a kaon plus one, which is labelled just down here. You've also got a sigma plus, or positive sigma if you like. So you'll often get a table with these that sort of says what the symbol is, the baryon number, the muonic lepton number here, tauonic lepton number, and the charge. So if this is actually going to be a workable equation, if you like, all those conservation laws should be obeyed. So if we just try this by charge first of all, the charge in a pion would be +1. Okay, so you've got a +1 charge here. You've got a proton, which we know has got a +1 charge. So altogether you've got +2 in terms of electronic charge on this side. On the other side, you've got a kaon particle here, which is a K+, which has a charge of +1. You can see down the bottom there, and that's going to be +1. And the sigma plus, the positive sigma here, shown in the second bottom row there, is also a +1 charge. So in terms of charge, you're okay. So if we look at baryon number now, as a baryon, this is not a baryon, 0. Okay, the proton is a baryon. All right, got a baryon number 1. If you look at the other side there, you've got the kaon particle, which has got no baryon number there. You can tell down here, so that's 0. And the positive sigma particle here has got a baryon number. So therefore, you check on baryon numbers there, it's 1 and 1 on each side, so that's okay. So let's just try lepton number now. You've got a pion particle here, which is your pion plus there. So that's not a baryon, it's got no muonic lepton number and no tauonic lepton number. So it's 0 for lepton numbers, and that's all net lepton numbers. And proton itself has not got a lepton number either. Okay, so it's 0 on one side there. If you check out the K plus one, the K-on plus one, this one here, on the bottom row here, has got just a charge, but it's got no lepton number. And the sigma plus the positive sigma one also has no lepton number either. So again, your lepton numbers are conserved here, so that's not an issue. Now, we try another one out here. You've got a pion here, which is changing into a muon plus particle there, okay, and also a neutron. All right. So again, if you check out the charge here, you'll find that the pion plus has got a charge of 1. This has got a charge of 1. That's got a charge of 0. So 1 on each side is going to be okay for charge. All right. So in terms of baryon number, this pion, if you check it, it's got a baryon number of 0. And on the other side, do we have a baryon number of 0? We've just got to check that out. A muon has got a baryon number of 0. Okay. But a neutron has got a baryon number of 1. So therefore, baryon number is not conserved here. So this would not be a possible reaction. All right. You could check lepton number as well, by the way. Here you see the lepton numbers. So it's got a muonic lepton number of 0, a tauonic one of 0, and it's got a lepton number of 0. So that would be there. If you check the other side, in terms of lepton number, the muon plus particle here the anti-muon, okay, would actually be -1 lepton number, -1 muonic lepton number, plus 0. So in actual fact, that wouldn't be conserved either. The lepton number wouldn't be conserved either here on this one, because it's going from 0 to a total of -1. So let's just look at one more example here. Let's look at the tau particle here. So this has got a negative charge, so this is a typical tau particle there. You can think of it as being the heavier version of the electron there. So the tau particle, if we go from lepton numbers first this time, this will have a lepton number of, checking it out, 0 for the muonic lepton number. It'll also be 0 for the lepton number. And it's got a +1 for the tau lepton number. So if you look at that there, it's a +1 in terms of a tau lepton number. All right, the tau particle lepton number here is 1. Okay. On the other side here, you've got your antipion here, because it's actually a -1 there. All right, so antipion here, so you've got a negative charge there. And in terms of lepton numbers, though, it's got no lepton number if you check it out. Okay, and it's got none for the electron one either. So there's got no lepton number there. All right. If you check the pion or the neutral pion one out here, this one in the second row, that's also 0. And the lepton number here at the end here, this is a tau neutrino, so it's in the right family, if you like, or the right generation. It's in the tau range. What's the lepton number for this tau one here? So if you check it out, the tau neutrino here has got 0 for the muonic lepton number, but it's got a +1 for the tauonic one. So you've actually got one there for your tau. So you've got a tauonic lepton number there of 1, +0 +0, which is 1. And on the other side it's 1. So in terms of that, it works. Okay. None of these are baryons you'll find. They've all got baryon numbers of 0 if you check them all out on the table. So in terms of baryon number, it's all balanced. And in terms of charge, if you check that out, you've got a -1 charge here. If you go and look at it there, which is tau1, which is just here. Okay. At the end, and you've got a -1 there on your antipion. All right, so charge is actually conserved. So this one would work. All right, thank you.